Good afternoon.
Good afternoon, ma'am.
Good afternoon. So yesterday, due to the network issue, I could not complete your class. So I don't know how much person I have covered yesterday. So this one I have discussed or not, mixing of two fruits.
Yes,
Anyone
ma'am,
know?
discussed. Yes, ma'am, discussed.
So up to this, I think this one also it is discussed. Maximum work obtainable, right?
Ma'am, this was not discussed.
Okay,
See,
okay,
okay.
okay,
Yes.
okay, okay, okay. Fine. So I'll discuss this part, then we will go for the discussion of the entropy generation for the closed and open system. So how the entropy will be generated in case of the open and closed system, that we will discuss in later part. So last class I was discussing up to the entropy principle application in case of the mixing of two fluids, right? So then I was discussing this maximum work obtainable from two finite bodies at temperature T1 and T2. Okay, so suppose we want to produce the work from the two bodies which are at different temperature, T1 and T2 temperature. So in that case, what will be the range of temperature to produce the work from these two body? Okay, so in this case, if you are observing here, we will have the body 1 which is at the temperature T1, and this is another body which is at the temperature T2. So initially what we are observing, so initially we have taken uh, that your these two body both are identical bodies, okay, finite bodies. So these two will have the constant heat capacity. So C will be the Cp or whatever it may be. Cp will be the constant in this case. Suppose for both the two bodies. Mm, okay, so in this case, initially suppose these two body are in contact with each other. So both are in thermal contact. So as T1 is greater than T2, so in that case, there will be the heat transfer from the body 1 to body 2. Okay, so after some time, there will both body will be in thermal equilibrium, and both will achieve the final temperature, that is your TF temperature. So that TF temperature that we can represent as T1 plus T2 upon 2. Okay, so there is only the heat transfer, but there is no work transfer because there we have not discussed any heat engine. Okay, So only both the bodies are in contact, thermal contact. So they both will be achieved one final temperature, that is a TF temperature. So initially, as we have not incorporated this heat engine, so there we will not find any work. So there will no work, right? Only both will attain a final temperature, that is the TF temperature, where your the that can be represented as T1 plus T2 upon 2. Okay. So next, what we are doing, suppose we want to extract work from these two body. So in that case, what we will do, we will operate a heat engine between these two bodies. So body 1 and body 2. So we will operate the heat engine. So here it is the heat engine. So which will draw the Q1 amount of heat from the body 1, which is at the temperature T1. Then it will transfer the work. Okay. Then some heat will be rejected to the body 2, which is at the temperature T2. So likewise, the heat engine will extract work from the body, extract heat from the body 1, and it will perform the work output. So that work output can be achieved to up to the certain limit. Up to the certain limit means when your temperature T1 will approach TF temperature, that is the final temperature, and T2 will also achieve the TF temperature. At that point, we can obtain the maximum work from the heat engine. After that, we can say that there will be no work delivered after achieving this TF temperature. Okay. So engine will stop working when the temperature will achieve approach to the final temperature, that is your TF temperature. Okay, so here that one only we are uh, going to find out that at which temperature we will obtain the maximum work from the heat engine. Okay, so when it is operating between these two body. Okay, so for that here. Okay, so here it will be the delta S universe. So in this case also we will apply the entropy principle to find out the maximum work. So first we have to find the what is the entropy change in case of the body 1. Then we will find out what will be the change entropy transfer in case of the body 2. Okay. So if you are observing in this case, the delta S1 is nothing but it is the entropy transfer for the body 1, in which your T1 temperature will approach TF temperature. Okay, so then in this case I have written only C dt upon T, or you can write Cp dt as per your desire. Okay, so C is related to the heat capacity. Okay, okay, it is related to the heat capacity. Heat capacity means in that case MCP we are taking, that is a capital Cp. Okay, so capital C. Okay. So in this case, C dt upon T will be equal to C ln TF upon T1. Similarly, in case of your body 2, in that case, there will be the entropy change, so that we have written like this. So it is the integration of C dt upon T. So where your temperature will from T2 to TF, and this will be equal to your C ln TF upon T2. So as for the entropy principle, these two entropy transfer will be added. So delta S universe will be equal to delta S1 plus delta S2. So here another term will also come, that is the entropy of working fluid, where entropy change in the working fluid. So working fluid, in case of the heat engine, in that case all of you know that that will operate in a cycle, है कि नहीं? साइकिल में अगर ऑपरेट करेगा तो वर्किंग फ्लूइड का एंट्रोपी चेंज क्या होगा? Anyone of you?
Zero.
Zero.
Zero. Okay, very good. So that entropy transfer will zero. So that's why we are not considering in case of the delta S universe. Okay, so we can say that so there may not be any entropy change. So entropy cyclic integral of the entropy will be zero. So as per the entropy principle, we have considered these two only. Then we have added. Then we have got this relation, that is the C ln Tf square upon T1 into T2. Okay. So then we have to find out what will be the final temperature at which your maximum work will be obtained. So in this relation, if you are observing in this case, delta S universe is always greater than 0. Okay, so it will be always in increasing order, and it will be the maximum at the reversible condition, or it is the when it is the constant. Uh, so in that case, your entropy change will be the maximum. So for the maximum work for the maximum work, so we have to use this term, that is the delta S universe is equal to your 0. So delta S universe is this one. So that is your C ln T square upon T1 upon T2 is equal to your 0. So 0 means it is a ln 1. So if you will cancel out this term, then you will get final temperature, that is your Tf is equal to your root over of T1 into T2. Okay, so this is the required temperature at which we will obtain the maximum work. Okay, so then we can say that the range of temperature at which we can obtain the maximum work from the two finite bodies will be this one. So at this condition, there is no work because heat engine we are not using. In this case, there is the maximum work output from the heat engine. So that final temperature is the root over of T1 into T2. Then we can write our maximum work will be the how much? ओके, यहाँ पे हमने मैक्सिमम वर्क का इक्वेशन नहीं लिखा है, तो मैक्सिमम वर्क विल बी योर Q1 minus Q2, right? Q1 minus Q2 means in that case Q1 will be the how much? Q1 will be the Cp T1 minus Tf, right? So similarly T2 Q2 क्या होगा? Q2 will be the Cp Tf minus T2. Okay, got my point? Then what will be the W max then? W max will be the Cp T1. This will be the plus T2. Then it will be the 2Tf. Okay. So in place of the Tf, we can put root over of T1 into T2, square root of T1 into T2. So this will be T1 plus T2 minus T2. So this is the maximum work obtained in case of your uh, two finite bodies. So this can be equal to क्या होगा अगर इसको
CP root
Root
T1
over
minus
T1
T2.
minus root over T2 का whole square.
T1 minus T2 to whole square. Okay, so this will be the maximum work obtained in that two finite bodies. So similarly, many more examples are also there. So where you can use this entropy principle, and then you can find your objective. Okay, so um, I can give you those examples so you can do it by yourself. Then we will go for the entropy generation. Okay, so before going to the entropy generation, what is that one? That we will discuss later. First, I think all of you have got the clear-cut idea how this entropy will be transferred. So all of you should remember this one. Entropy will always transfer with the heat flow. Okay, so if there is the heat flow, so in that case, there will be the entropy transfer. So another case is that due to that heat flow, there will change of the internal. There will be the increase of the internal irreversibilities, and because of that you can experience the entropy increase due to the internal irreversibility. So there we can say that is related to the irreversible process, and because of that irreversible process there will be the entropy generation. So entropy transfer with heat flow, that we were writing that equation. Suppose it is your system, then we are having the surrounding, so it is the system and it is your surrounding. So suppose the surrounding is at the temperature T0. So there is the heat transfer from the surrounding to system. So suppose at the system boundary there is the heat transfer. Q amount of heat is transferred to the system. Or let us take it is leaving from the system, whatever may be. If it is entering to the system, then it will become positive. If it is leaving from the system, then it will become negative. So initially let us consider it is the heat flow into the system at the at the constant temperature, which is your surrounding temperature, that is your T0. So because of that one, what will be the entropy change? So entropy change in the system will be, in this case will be the, it will be the अगर ये entry हो रही है, so in that case that will be the Q upon T0. Okay, surrounding का क्या होगा? Surrounding का it will be the negative one, so it will be the Q upon T0. So in this case, the entropy will decrease in case of the surrounding, and system it will increase. So similarly, suppose there is the heat flow out from the system, and it is an flow out from the system to the surrounding. So in that case, the system will have the negative value, that means entropy is decreasing, and for the surrounding it will be the positive one. Okay, so that will be the Q upon T0, so it will increase. Okay, so here this entropy transfer is possible due to the heat flow, but there is no entropy transfer associated with work transfer. Okay, so there is no entropy transfer will be associated with the work. Okay, suppose any system we are considering which will deliver the work. Okay, and that will be stored in the flywheel. So in case of the flywheel, that energy, that molecule are placed around its axis. Okay, so that is there. That molecule will be placed in such a way that that will be we can say there is no dissipation will occur, right? In that case, energy dissipation will not occur, means that will be at the perfectly arranged condition. So there will, because of the no dissipation, there will no uh, entropy increase. Okay, so that we can say that there is no entropy transfer associated with the work. So now we will discuss the entropy generation. What is that one? So entropy generation in place of the open system and closed system. So what is entropy generation, that I will discuss. Then I will go for the um, application to the closed system. Okay. So entropy is nothing but it is your molecular disorderness or molecular randomness. So it will increase when the process is more irreversible. So in that case, more entropy can be generated. So entropy for the closed system or any system, it can increase both ways, two ways. Uh, दो वे में इंक्रीज कर रही है. So one is your due to the heat transfer, heat transfer. Okay, so um, another one is your due to the internal irreversibilities. So internal irreversibility effect means in which your kinetic energy will be dissipated into the internal energy increase, or we can say that work is your it will dissipated into the internal energy increase. So in that case, your internal irreversibility will increase the entropy. So these two ways will be discussed in case of both open system and closed system. So by these two ways, your entropy will generate or entropy will increase within the system. So let us take, by taking one example, we'll discuss. So let us take there is the infinitesimal heat is transferred to the system. So it is your system. Okay. So infinitesimal heat is transferred to the system. So which is at the temperature T1, sorry T. So which is the equal temperature with the surrounding. Okay, so for this one, suppose we want to write down entropy transfer. So that will be the ds is equal to your des plus dis. So des is nothing but it is your entropy increase due to the external heat interaction. So this is the external heat interaction. So that equation we can write as dq upon T. Okay, so this is for external heat interaction. The what will be the entropy transfer? Then DIS is nothing but it is the internal due to the internal irreversibilities. What will be the entropy increase? Okay, so that is your DIS. So this entropy changes due to the internal irreversibilities. Okay, so ds is always greater than your dq upon t, and dis is always greater than equal to 0. So entropy generation or entropy can be increased due to the internal irreversibilities. So in which your uh, kinetic energy will be dissipated into the increase of the internal energy. Okay, so this is known as your, this term is known as your S generation or entropy generation. So entropy generation is nothing but it is the entropy increase due to the internal irreversibility. Okay, so that is known as your S generation. Okay, I think now it is clear to you. So suppose we want to find out for the closed system. what will be the S generation, that we have to find out. So for the closed system, in that case, suppose there is both reversible process and irreversible process is occurring. So suppose there is the infinitesimal reversible process. In that case, we can write our equation. So dq is the heat transfer or heat interaction. So it is for the reversible process I'm writing. So if it is a process, then we can write the first application to the process. So that equation is dqr is equal to your dur plus dw, right? Suppose the process is irreversible. In that case, your equation will be the dqi. I is represented as irreversible process is equal to your dui plus dw. Okay, so if you will observe in these two equation, so this two will be remain same because u is the property of the system. So in that case, we can write as dur is equal to your dui. If it both are equal, then this equation we can write as. So in case of the first, instead of dur, we can write as dqr minus dw. So it is the reversible process. So in that case, we will put the PDV relation. Then it is the irreversible process. In that case, that work will not be the PDV relation. Okay. तो ये है इरिवर्सिबल, ये भी इरिवर्सिबल. तो यहाँ पे हम इसको ऐसा लिख सकते हैं डी क्यू आर माइनस पी डी वी इज डी क्यू आई minus dwi. Okay, so if we are dividing the temperature, then it will be the dq upon t in the reversible process minus pdv upon t dqi upon t, or we can put it outside I minus dwi. So if you are bringing this term to the right hand side, then it will give us dq upon t r is equal to your dq upon t I minus pdv. So it will become plus, right? Plus pdv minus dw t. Okay. So the equation will be the pdv minus dw. Okay. So if you are observing this term, so this one will be the heat transfer. If it is in reversible process, then it will lead to the entropy transfer in the reversible process, that is your ts. Then it is due to the irreversible, then that we can write as due to the external irreversibility, that will be the des. Okay, and this term is known as your energy lost or work lost due to the irreversible process or irreversibility. So this is known as your work lost. Okay, or lost work we can say. So this is also one type of that it is the dissipation of work into the increase of the internal energy, right? So this is entropy change due to the internal irreversibility. So this term is known as your S generation. Okay, so entropy generation, this one. So lost work is nothing but it is um, associated with the internal irreversibility. So this is your entropy generation. So then whole thing we can say that it is the entropy transfer in case of the closed system, where it is the addition of DES and DIS. ओके, ये क्लोज सिस्टम के लिए ये इक्वेशन आप यूज कर सकते हो. Got my point? Then we can discuss the further open system. अगर उसको more simplify करना चाहते हैं, as per the second law, we all know that entropy changes S2 minus S1 is greater than equal to your dq upon t. So where there is the change of the process 1 to 2. Okay. So S generation in case of the closed system, we can also write as, so it will be the difference of the entropy change, that is your S2 minus S1 minus here there is the entropy transfer, so that will give you the entropy generation. Okay, ठीक है. इसको अगर इधर ले आते हैं, ये है आपका entropy generation, right? So we can write this as it is your entropy change in the reversible process, and this is the entropy transfer due to the heat interaction. It is your entropy generation. So we can also write in this way for the closed system. So one thing is, if the reversibility is more, then your um, or entropy generation will be the more. Okay, got my point? So this is for the closed system. Then we will discuss for the open system. Okay. So open system means there will be the transfer of both mass and energy. And in this case, as we are discussing entropy generation, so then here also there will be the entropy transfer and entropy generation due to the internal irreversibilities. Okay, so that transfer can be achieved with the help of your fluid motion entropy transfer will be achieved due to the fluid motion that we'll discuss. So open system means we can write as Mi is your amount of mass transfer. Then Me is nothing but it is amount of mass exit from the control volume. So this will be the control volume. So it is the control surface. Okay. So at this surface, let us consider there is the infinitesimal or there is a heat transfer, finite amount of heat is transferred. So if it is a finite amount, then we can write as the Q. Suppose in this case the rate of all are represented in the red form. So here also will represent the rate of heat transfer. So that is possible at the constant temperature, that is your T. So then your entropy transfer will be the Q dot T, right? So let us consider there is the shaft work. So that shaft work is, let us consider that is the rate of shaft work is taken as W dot SH. Okay. Now for this, we can write the continuity equation. So what was your continuity equation? If it is a steady flow, please tell me. क्या था कंटिन्यूटी इक्वेशन? हमने स्टेडी फ्लो एनर्जी इक्वेशन में डिस्कस किया है.
A1 V1 equal
A1
to A2
V1
V2.
equals A2 V2
A1 V1
equals A2
Equal
V2.
to A2 V2.
ये ठीक नहीं है, ठीक से बताइए।
Volume rate flow is constant.
Volume
मैम
flow is constant.
A1 V1
Okay.
by small V1, A2 V2 by
Okay.
small
So
V2.
continuity equation will relate to the mass transfer. Okay. Got my point. So that is the whatever rate of mass is the mass flow is entering to the
Mm.
system. So that will
O1
equal
is
to the whatever amount
rho
of
AV
mass
plus
is
constant.
right.
Mm.
So okay. So what are your numbers?
91.
Okay.
69.
9.
16,
92.
60.
69.
69, 91, 69,
92.
then 6,
Ma'am, 9.
92, 9,
Ma'am, 60.
मैम
60.
40.
Okay.
92.
44.
सबने आंसर दिया? Okay. Let us continue. If it is the steady flow, then we can write as the mass flow rate, which is entering to the control volume, is equal to the mass flow rate leaving from the system. If it is the steady flow, steady flow. If it is the transient flow or it is varies with time, then we can write the uh, or variable flow process. Okay, so in that case the equation will be the whatever the amount of mass is entering to the control volume, in so that will be mm, okay. So this two difference is known as it is the net mass transfer.
Then we are considering incompressible flow. No?
Uh-huh.
Or
Net mass transfer will be equal to your we can say that rate of mass accumulated in control volume. हाँ, जब हम स्टेडी फ्लो कंसिडर कर रहे हैं तो ये इक्वेशन यूज होगी. जब हम ट्रांजिएंट फ्लो कंसिडर कर रहे हैं, so in that case your net mass transfer will be always equal to the rate of mass accumulated within the control volume. Okay, so this is your continuity equation. So similarly you can write down your energy equation. If it is the energy equation, in that case all the form of the energy will be considered in this equation. So if it is the steady flow energy equation, then both energy which is entering to the control volume is equal to the leaving from the control volume, so both will be equal. But if it is the transient flow, so in that case that equation we can write as okay. So there will be the net rate of energy transfer will be equal to the rate of energy accumulated within the control volume. So that one we have to write down. So ये आपका mass है, mass will be multiplied with h into v2 square upon 2 plus gz. Okay, then it is at the outlet condition, this will be the MA exit condition. Okay, so this will be the, so this is I, so it will be the infinity, right? है ना? तो जो भी हो आप जितना ले सकते हो, 1 2 3 4 जो भी हो exit. तो बेटर हम इसको ना लिखे तो ठीक है, ना लिखे तो ठीक है. Okay, so this will be the h plus v2 square upon 2 plus gz plus q rate of heat transfer minus your shaft work, that is dot. So this will be equal to your del E upon d tau. So this one I have written for the transient flow or variable flow process. So in this case, it will be the energy equation will be the net rate of energy transfer is equal to the net rate of energy accumulated in control volume. Okay, so this is your energy equation. If it is a steady flow, तो ये टर्म आपकी नहीं रहेगी, ये जो डेली अपन डी टाउ है, ठीक है, बाकी ये सब इक्वल हो जाएंगे, ठीक है. What my point? Steady flow energy equation अगर आपको याद होगी, तो वहाँ पे हम whatever the energy is entering, that we are taking the exit equal ही ले रहे थे, ठीक है. So in case of the open system, we will consider the entropy principle. Okay, as for the second law of entropy principle, there we can write our um, what will be our entropy change or entropy transfer. Then that we will discuss. So ये आपका open system हो रहा है, means यहाँ पे आपका जो है due to the mass transfer there will be the entropy transfer also, irreversibility increase होगी, so it will be the Si. Okay, so similarly for the exit also we can write as m dot e Se. Okay, so ये है आपका net rate of entropy transfer. Okay, then here due to the heat interaction there will be the entropy transfer, so then whole system is known as your net rate of entropy transfer. Okay, so which is less than your ds upon d tau. So it is your rate of increase of entropy of the control volume. So this is due to the internal irreversibilities. Okay, so internal irreversibility की वजह से जो हो रही है entropy change, that is known as your entropy generation. Okay, what my point? So this is your rate of increase of entropy of the CV, means whatever the entropy is increased due to this flow of the mass of the fluid and their heat interaction, that will be always less than this term. Okay, so entropy generation within the control volume we can write down. तो ये सब जो हम डिस्कस कर रहे हैं ये वेरिएबल फ्लो के लिए है, ठीक है, और वेरिएबल फ्लो और ट्रांजिएंट फ्लो. Okay, so which will varies with the time, so that is the variable flow. So the entropy generation within control volume due to the due to the irreversibility, so that we can write as, so all we have represented in terms of the red form, so that S generation also we will represent in red form. So this is the less data, so this we can represent it as तो अगर हम इंटरनल irreversibility के हिसाब से कर रहे हैं, so this we can write as ds upon d tau. So all will go to this side and this will be, because S generation is always greater than 0, so इसको अगर हम इधर ले रहे हैं, so that will it will give you the entropy generation. So ये है आपका इधर, so this will be the m I s I plus, so this one is the S generation in case of your open system. So here it is always greater than, S generation will be always greater than equal to 0. ओके, सो ये है हम जितना भी डिस्कस किए हैं ये वेरिएबल फ्लो के लिए है. सो सपोज इट इज द स्टेडी फ्लो, in that case as we have written in this case continuity equation it will be same, then energy equation will become the q dot minus wsh plus mi h plus square root into plus gz I minus will be equal to 0, then it will be square upon 2 plus gz plus q dot is equal to your, ये राइट हैंड साइड आएगा plus, so this will be the energy equation. Okay, so then entropy transfer will be, or entropy equation will be, so this equation 1 will become, ये टर्म 0 हो जाएगी, ds अपन deta राइट, तो ये आपका 0 हो जाएगा, then what will be the S generation? So S generation will be your S generation will be how much? So this will be minus q dot t, right? Okay, plus यहाँ पे mi okay, so this will be the minus and this one will be the plus, right? mi plus हो जाएगा, this will be the minus. Okay, so we can write as it will be the MISI minus MESE minus Q dot T. Okay, so entropy equation will be this one. Okay.
मैम आई वाला माइनस है ना?
जी, tell me क्या
मैम
बोल
यहाँ
रहा
पर एम आई माइनस में रहेगा ना, नीचे वाले जो
एम आई
equation है।
माइनस में है।
हाँ, ये माइनस में रहेगा, mi माइनस में, ये प्लस में रहेगा. ठीक है,
आपने उधर एम आई को माइनस कर दिया।
हाँ, ये माइनस ये प्लस में रहेगा. ठीक है. Okay, so this will be the for the steady flow entropy equation. So likewise we can also find out what will be the entropy equation if there is the one inlet and one exit of the fluid. So in that case what will be the equation? So that one also we can write down. So one inlet and one outlet means in that case your entropy change also we can write as Then in that case, your entropy equation will be reduced to your S2 minus S1. Okay, so entropy change. So that will be your Q dot upon T plus S generation. Okay, what my point? So this will be the for the one fluid which is entering and leaving from the system, that entropy change equation will be this one. Okay. So as per your problem, you can use your equation. Then we have to find out the reversible adiabatic work. So स्टेडी फ्लो एनर्जी इक्वेशन आपको अगर याद होगी, अगर हम डायरेक्ट फॉर्म में उसको लिखते थे तो क्या लिखते थे? सो डी क्यू प्लस योर जो है एनर्जी को हम कैसे लिखते थे? डी एच, है ना? याद है कि नहीं? Okay, we will write down again. Okay, so suppose there is the heat transfer, heat interaction in infinitesimal heat interaction, that is in case of the reversible process. Then that equation was H1 plus V1 square upon 2 plus Gz, right? Plus dq is equal to your H2 plus V2 square upon 2 plus Gz. If there is a software that we can write as dwx. Okay, इसको अगर dq को इस side में ही रख लेते हैं, then it will be this term, if you are bringing to the right hand side, then it will become s2 minus h1, right? Then your v2 square upon 2 minus v1 square upon 2, then it will be the it is gz1 gz2, then this will be the gz2 minus gz1, right? Plus dwx. So this one in differential form we can write as, this will be the dh, right? This term, and this will be the v dv, right? And this term we can write as g dz plus dws, right? So this is in differential form, where we have written this equation for the unit mass basis. This is the steady flow energy equation. Okay, so in this case, your heat transfer is equal to your dH plus VdV plus GdZ plus dWx. So all of you know that in case of the reversible process, your heat transfer will be equal to your TdS, right? dq upon T is equal to your ds. So that is only in case of the reversible process. Then this equation 1 will become TdS is equal to your dH plus VdV plus your GdZ plus dWx. So this is applicable only for the reversible process. So in this case, suppose we will put the property relation in this place of the TDS. So there is the two relation of TDS relation or property relation. One is your TDS is equal to your DH minus VDP, right? For my point, another one is the uh, भूल गए हो शायद सारे के सारे। बोलो क्या था? TDS is equal to
DU
DU plus
DU
P
plus
D.
PdV.
Right.
PdV
Who has given the answer?
92.
Okay. So here we are having the two relation of TDS. So this is also known as the property relation. Okay. So property relation means your H is also property, DS is also property, T is also property, V is also property, P is also property. Okay. So in place of the TDS in equations, let us take it as equation 2. In place of the TDS, suppose I have taken this DH minus BDP, then DH and DH will get cancelled, then only we will have the BDP term. So we can write as minus BDP. I have omitted one line, so you can write that one. So this will be equal to VdV plus GdZ plus dWx. Okay, I got my point. So now if you are integrating this term, then you will get it is the integration of minus VdP is equal to your this term will become your it is the change of del v square upon 2 plus I can write it is v2 square upon 2 minus v1 square upon 2. You can write this term also delta v2 v square upon 2. So this will be the g delta z plus your wx, right? So this will become wx or we can write as w12. Okay, w12 भी आप लिख सकते हैं, ठीक है. So suppose you are regulating this term, kinetic energy term and potential energy term, then you are getting the work that is the shaft work will be equal to your minus um, integration of BDP. So that is from the process 1 to 2. Okay. So suppose as it is mentioned, it is the reversible adiabatic work in the steady flow. So reversible work, we have achieved this equation. If it is the adiabatic, so in that case, all of you know that dq term will be the 0. Okay. So if dq term is 0, then your equation that this equation in place of the TDS, this will be become your 0, right? This term 0 हो जाएगा, ठीक है. अगर ये term 0 हो रही है, then this DH will be equal to your BDP. So TDS is equal to your DH minus VDP, right? So suppose your DQ is your 0, in that case the TDS will 0. So TDS will be 0, then this will be the DH is equal to your VDP. So as suppose we are taking the integration, then it will give you the integration. Suppose the process is occurring a 1 to 2, dH is equal to it will be the VDP, right? So this I can write as H2 minus H1 is equal to your integration of 1 VDP for the process 1 to 2. Okay, so here we have got another relation. If you are comparing this, let us take this is the equation 3 and this one is the equation 4. So if you are comparing this equation 3 and 4, then we can write as our work in case of the reversible adiabatic will be Ws will be equal to your minus VdP integration, means this will become H1 minus H2, right? It will become H1 minus H2. So I can write this reversible adiabatic work that will be H1 minus H2, or it is integration of your VdP 1 to 2. Okay. Got my point? अगर आपको शॉर्ट क्वेश्चन भी कोई पूछेगा कि रिवर्सिबल adiabatic है, उसमें वर्क क्या हुआ, यू कैन राइट दिस वन, ठीक है. So this VDP is nothing but if you are considering in PV plot, that will be in reverse direction. Okay, so you can derive up to this. Fine. So now entropy chapter is completed. So we are having some available part also, available energy or availability. So I will discuss a little bit only for that available energy. Then we will go to our gas power cycle. No need to write irreversibility. So next chapter is our availability or available energy. So in case of the IC engine, suppose it is the petrol or diesel engine. So in that case, the some amount of fuel energy is utilized to produce our work, and rest will be available as the excess gas temperature. Okay, so that amount of energy which are utilized to produce work, so that is known as your available energy. So that we are going to discuss. So how this is related to the uh, your irreversibility or irreversibility process, so that we'll discuss. Okay, so availability means the available energy only. So that is uh, the term we have used. So यहाँ पे हम लोग डिस्कस करेंगे कि अवेलेबल एनर्जी साइकिल में क्या हो रही है, प्रोसेस में क्या हो रही है, राइट. So that one we'll discuss. So that will give one relation with the temperature as well as the maximum work and heat transfer that we are going to see. So all of you know that there are the two terms so that we are always using in case of the thermodynamics. So one is your high grade energy. Another one is the low grade energy, right? So tell me what is the high grade energy and which one is the low grade energy?
वर्क
मैम
इज
ये
हाई
हाई
ग्रेड.
ग्रेड वो है जो ट्रांसफर करने पर उसका एफिशिएंसी चेंज नहीं होता, लेकिन लो ग्रेड है जैसे कि हीट को वर्क में चेंज करते हैं तो वो घट जाएगा एफिशिएंसी, तो वो
कंप्लीट
लो ग्रेड होता है।
ट्रांसफॉर्मेशन होता है.
Okay, so can you give me the example of high grade and low grade energy?
वर्क इज
वर्क.
हाई ग्रेड, हीट इज
What?
लो ग्रेड।
Okay, so I saw Agarwal. Your roll number is 48, I think.
14 मैम।
14.
Yes, ma'am.
Okay. So you are right that heat is your
Ma'am,
low grade
electrical
energy.
and kinetic energy are also high grade energy.
Jay?
Electrical and kinetic energy.
Yes, electrical energy, kinetic energy, wind power, water power. So those are our
Yes, sir.
high grade energy, and other the heat energy which are derived from the nuclear fission process. So which are derived from the fossil fuels. So those are all low grade energy. Okay. So already I have told you in second law. So the low grade energy is mainly utilized in many devices to find the work output. So, in that case, suppose the heat is derived from the combustion of fuel, so that energy is used in case of the petrol and diesel engine, right? So, in nuclear power plants, heat is derived from the nuclear fission process, so that is also low grade energy. So, the available energy means the part of low grade energy which will give you the work or which is available for the useful energy. So that is known as your available energy. Okay. So the part which is rejected to the atmosphere or to the river or pond or whatever it may be. So that is nothing but that is the unavailable energy. Okay. So high grade energy is your work and low grade energy is your heat. Okay, so here we are going to discuss the suppose the available energy it is produced in the cycle, so how that equation will be we will discuss. Okay, so when it is applicable to the cycle, there we are incorporating the heat engine, right? So suppose the heat engine is placed in the source and in between the source and sink. So let us say that source is temperature is T1. So heat will be drawn Q1 amount. So this will deliver the work. So maximum work is nothing but it is the available energy. Okay, so then we are getting the heat rejection to the sink, so which is at the temperature T2. Okay, so this minimum energy which is rejected by the to the sink is known as the unavailable energy. So we can write our maximum work in this case will be the available energy minus unavailable energy. So in short, I have written unavailable energy. Okay, so available energy is nothing but it is the W max. So W max we are telling as the available energy. Okay, okay. So please correct this one. So W max is nothing but it is the useful energy which is available at the heat engine shaft. Okay. So then this Q2 is nothing but it is the unavailable energy. So this Q1 we can represent it as it is the addition of your available energy and your unavailable energy, right? Then W max is nothing but it is available energy as I have told you, and unavailable is your Q2. Q2 है ना, इसको मैं लिख नहीं रही हूँ उसको. Then your W max can be represented as Q1 minus your UE. So this is the available energy which is your W max. Okay. So then let us consider that your efficiency in case of the reversible heat engine is how much. So reversible heat engine का हम किस तरीके से efficiency को represent करेंगे?
1 minus T2 by
1
T1.
minus T2.
Very good. Ayush, right? Ayush, your roll number is 19.
14, ma'am. 1 4.
1 4. Again, I'm getting confused. Sorry, sorry. Okay, thank you. So if it is a reversible heat engine and we are representing the efficiency, then your efficiency will be in terms of the absolute thermodynamic temperature scale. So that we can representing as 1 minus T1, T2 minus, sorry, T2 upon T1, right? So that is the reversible heat engine efficiency. Then suppose we are getting the maximum efficiency of the heat engine. So in that case, for the maximum efficiency, we can say that at the atmospheric temperature तक जब इंजन आपका रन कर रही है, जो टेम्परेचर सॉरी हीट रिजेक्शन कर रही है, उस टेम्परेचर तक अगर हम हीट को रिजेक्ट कर रहे हैं, so in that case you will get the maximum efficiency. Okay, so let us take T0 is the atmospheric temperature or surrounding temperature up to which that heat rejection is possible, and we will get the efficiency of the heat engine will be the maximum. So W max, eta max I can write as 1 minus T0 upon T1, right? So then your W max will be equal to your eta max कैसे हम represent कर सकते हैं? Eta max will be your it is the W max upon your Q1 heat input, right? So W max को हम कैसे represent करेंगे? It will be eta max into Q1. So this will be 1 minus T0 upon T1 multiplied with your Q1. Okay, so this is the maximum efficiency of the heat engine when it is operating in the cycle. Okay, refer to the cycle. Got my point? So similarly, suppose we are considering any finite process. So that is your in xy coordinate. So any finite process, let us take that is your x to y we have taken. So in this case, heat is supplied reversibly. So that amount of heat is, let us take that is, we have taken dq1, and heat is rejected as the dq2. Okay, so heat received is at the temperature T1. So for that one, suppose we have to write our W max, so then what will be the equation? Okay, so heat addition हो रही है. Then suppose in case of the TS plot also if you are representing, तो वहाँ पे हम लोग को heat transfer का details मिलेगा. So TS plot means in that case let us take that process we have taken x to y. Okay, so there is the heat addition Q. Okay, so heat is added in this case. Then your available energy we can find out in this diagram. Okay, so what is that one we will see. So let us take there is the atmospheric temperature is your T0 temperature. Okay, so up to which we can reject the heat at that temperature, and we can draw the maximum work. Okay, so that we are going to find what will be the unavailable energy or available energy in this case. So W max will be how much? W max will be, so in this case let us take it is the elementary heat addition dq अगर ले रहे हो, ठीक है, तो इसी के हिसाब से d W max होगा, right? So so let us take in this case your temperature is up to your T0 temperature, then this will be 1 minus T0 minus T1 Q1 और dq1 एलिमेंट्री जो हम लिए हुए हैं उसी के हिसाब से आपका t1 माइनस t0 अपन t1 dq1, right? So this I can write as dq1, here dq1 minus dq1 t0 t1. So this is dw max means it is the available energy, right? So available energy will be the dq1 minus dq1 t0 upon t1. So for suppose heat rejection mm, is possible at the t0 temperature, so then we will get the our unavailable energy will be here. So you suppose this one I am integrating, so this is your, so let us take that this process is x to y, so this will be the dw max is equal to your integration of x y dq1 x y your t0 t1, right? So in this case your this can be represented as qxy and this can be represented as t0 t0 को common ले लीजिए, this will be the dq1 upon t1, so this will be the entropy change, so that can be represented as sy minus sx. Okay, so this will be the w max. So in this case the available energy is your w max and it is your unavailable energy. So unavailable energy I can write as w max so this will be the minus, right? So यहाँ पे अगर माइनस होगा ये अगर प्लस होगा then this will be in reverse. It will be the qxy minus w max. So this one is your unavailable energy. So unavailable energy is also represented as t0 sy minus sx. Okay, so this is your unavailable energy. So unavailable energy is the product of the lowest temperature of heat rejection, that is your t0. Okay, so and this one is the entropy change. It is a multiplication of the lowest temperature and entropy change during the process. So available energy is nothing but it is the W max, and unavailable energy in the process we can write as it is the product of lowest temperature and your entropy change in the process. Got my point? So up to this I will discuss. So here there is two terms we will conclude here. One is the available energy, another one is the unavailable energy. Okay, so unavailable energy is also known as your exergy. So आजकल जो अगर रिसर्च पेपर कोई अगर पढ़ोगे तो देखोगे एक्सर्जी एनालिसिस ज़्यादातर किया जाता है. एक्सर्जी एनालिसिस मीन्स वहाँ पे हम कितना अमाउंट ऑफ यूजफुल वर्क ड्रॉ कर सकते हैं कोई भी एक सिस्टम से. अनदर वन इज योर एनर्जी. Okay, so it is the unavailable energy. Okay, so it is we are trying to reduce this energy to increase the exergy. Okay, so these two terms of energy mainly we are discussing in thermodynamics. Uh, uh, then in later part we will also discuss the what will be the quality of energy. Okay, so available energy in the open system and closed system, that we will discuss. Okay, so I will stop up to this. Okay, so available energy is your W max and unavailable energy जो energy आपका lost हो रही है वो जो इंटरनल इरिवर्सिबिलिटी वजह से या जो भी हो, ठीक है। ओके, so far we have discussed the property खत्म है, ये भी टेम्परेचर स्केल ये सब खत्म है, प्योर सब्सटेंस खत्म है, स्टीम डबल मैंने आपको बता दिया था ऑलरेडी। इक्वेशन ऑफ स्टेट में आपको यहाँ पे कंप्रेसिबल चार्ट भी थोड़ा थोड़ा बता दी थी, मोलियो डायग्राम में भी बताई थी। इक्वेशन ऑफ स्टेट ये एक दिन का क्लास होगी, अगर मैं लूंगी तो ये बच जाएगा आपका। ये टर्म आपका वंडरवल इक्वेशन ये ऑलरेडी आप लोगों ने पढ़ा है, फिर भी थोड़ा देखती हूँ, मैं बता दूंगी। ये फर्स्ट लॉ आप लोग का कंप्लीट हो चुका है और नॉन फ्लो प्रोसेस एंड फ्लो प्रोसेस के लिए। देन फर्स्ट लॉ ऑफ थर्मोडायनामिक्स ये एप्लीकेशन पार्ट भी खत्म हुआ है। सेकेंड लॉ में आप लोग का सारा के सारे कंप्लीट हो गए हैं। आज हमने डिस्कस किया अप टू द अवेलेबल एनर्जी एंड अवेलेबिलिटी। सेकेंड लॉ एफिशिएंसी तक डिस्कस करना पड़ेगा, तो मुझे 2 क्लास चाहिए होगा। देन वी विल डिस्कस द पावर साइकिल, ओके, रैंकिन ये गैस पावर साइकिल, ठीक है। तो इतने के लिए मुझे और एक 4 क्लास चाहिए। सो टोटल आई विल टेक 6 to 7 क्लास and I will complete the course. Okay. So I will take the extra class. So total 62 students are present. So it is better to take the attendance now. I'll take it today. Okay, roll number 1. Two. Please wait 1 minute. Roll number 1.
Present, ma'am.
2.
Present, ma'am.
3.
Present, ma'am.
4. 5.
Present, ma'am.
6.
Present, ma'am.
7. 8.
Present, ma'am.
9. 10. 11.
Present, ma'am.
12.
Present, ma'am.
13.
Present, ma'am.
14.
Present, ma'am.
15.
Present, ma'am.
16.
Present, ma'am.
17.
Present, ma'am.
18.
Present, ma'am.
19.
Present, ma'am.
20. 21.
Present, ma'am.
22. 22. 23.
23 present,
24.
ma'am.
24.
I'm 23 present.
24.
Present, ma'am.
25.
Present, ma'am.
26.
Present, ma'am.
27. 28. 29.
Present, ma'am.
30.
Yes, ma'am.
31.
Present, ma'am.
32.
Present, ma'am. 32.
33. 33. 34. 35.
Present, ma'am. 34 present.
35.
Present, ma'am.
36.
Present, ma'am.
37.
Present, ma'am.
38, 39,
Present, ma'am.
40,
40 present.
41,
Present, ma'am.
42,
Present, ma'am.
43, 43, 44,
Present, ma'am.
45, 45, 46, 47, 48,
Present, ma'am.
49,
Present, ma'am.
50, 51,
Present, ma'am.
52, 53, 54, 55,
Present, ma'am.
56,
Present, ma'am.
57, 58, 59, 60,
60 present, ma'am.
61, 61, 62, 63,
Present, ma'am.
64,
Present, ma'am.
65, 65, 66,
Present, ma'am.
67, 68, 69,
69 present, ma'am.
70,
70 present, ma'am.
71, 72,
Present, ma'am.
73,
Present, ma'am.
74,
Present, ma'am.
75,
Present, ma'am.
76, 77, 78,
Present, ma'am.
79, 80, 81, 82, 83,
Present, ma'am.
84,
Present, ma'am.
85, 86,
Present, ma'am.
87,
Present, ma'am.
88,
Present, ma'am.
89, 89, 90,
Yes, ma'am.
91,
Present, ma'am.
92,
Present, ma'am.
93,
Present, ma'am.
94,
Present, ma'am.
95, 96, 97, 98, 99, 100,
Present, ma'am.
101,
97, ma'am. Hello.
101.
Hello. 97, ma'am.
Okay, okay. 101, 102,
102
103,
present, ma'am.
103 present,
103,
ma'am. 103
104,
present.
104
104,
present.
105,
105.
106, 107,
Present, ma'am. 107.
108, 109,
Present, ma'am. 109.
110, 11,
Yes, ma'am.
12,
112 present, ma'am.
113,
Present, ma'am.
114,
Yes, ma'am.
115,
Present, ma'am.
116,
Present, ma'am.
117,
Present, ma'am.
118,
Present, ma'am.
119,
Present, ma'am.
120,
Ma'am, she got disconnected right now and unable to join. She is facing problem with Wi-Fi.
okay.
Ma'am, 77 present. Mic issue.
Why? Why mic issue? 121,
Present, ma'am.
122.
Present, ma'am.
Okay. So I'll take 6 to 7 class more. So Ritika, tomorrow please arrange the class for me. What time I can take?
Okay, ma'am.
Excuse me,
Okay.
ma'am. Roll 33, ma'am. Present.
आप अपने टाइम में क्यों नहीं दिए?
मैम माइक ऑन नहीं हो रहा।
क्यों नहीं ऑन हो रहा था? पहले से ऑन करना चाहिए।
मैंने ऑन किया फिर आप पार हो गए तो डिस्टर्ब नहीं किया।
ओके, सो नेक्स्ट सैटरडे को भी आप कर लीजिएगा, है ना? ठीक है।
मैम 34 प्रेजेंट।
I'm
प्रेजेंट।
roll 9.
क्या
मैम
हुआ फिर?
95।
सबको प्रॉब्लम हो रही है, क्यों? ओके, थैंक यू ऑल।
थैंक यू मैम।
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
थैंक यू मैम।